Hello everyone and welcome to our session, this video for EECE210 Quiz 2 material. Today we're going to solve a lot of important problems that are really beneficial for the exams, and this video is part of a series which is an initiative by the Cultural Club of the South to support students during these challenging times. So anyways, this session is extremely important and it has problems selected from EUB previous exams and course questions, and understanding these problems is really important for Quiz 2 because a lot of the problems are repetitive and have similar ideas basically. So, in my opinion, this session is extremely important. Anyways, let's begin. Here we have a formula sheet. It has most of the ideas used for Quiz 2. I believe anything that isn't mentioned here is extremely important for you to know how to use without a formula sheet. But in general, this encapsulates everything you need to know. Anyways, let's begin. So we have here in problem 1, find the Thevenin equivalent circuit as seen from terminals A and B, the open circuit. So for Thevenin, for any question for Thevenin, it goes like in general. Here we have like the Thevenin circuits. Okay, before we even start, let me explain this. We have three cases. We have case 1, we have case 2, okay, and we have case 3. Okay, so in case 1, which is the case in problem 1, as we see here, the thing with problem 1 is that we have two independent sources. We have the 7-volt independent source and the 1 ampere independent source. So when the circuit has all independent sources, so there isn't a source which is dependent, everything is independent. Okay, this is gonna be case 1. Case 1, which is all sources are independent. They function without any intervention from the other elements of the circuit. So in this case, the procedure is as follows. So step 1 or step 2, really, it doesn't really matter. Find our Thevenin by deactivating the sources. What I mean by deactivating the sources is that if we have a voltage source, okay, it's gonna be a connecting wire. So the way we deactivated it is that the voltage source gives us voltage, but the connecting wire is 0 volts. So it's basically not even there. And if we have a current source, this is gonna be an open circuit. In this case, we deactivated the independent sources, and we can find our Thevenin the same way we use our equivalent from quiz 1 material. So, and then after we find our Thevenin, we find it by the usual means, like from quiz 2 we do our equivalent parallel series, whatever. In step 2 we find V Thevenin. How? In this example, finding V Thevenin is basically keeping the circuit as it is. So bring back the sources, bring back everything. This is our circuit. Our target is to find the voltage in here, V Thevenin, between the open circuit terminals, so between terminals A and B. And we know how to get this, really. We can use node voltage, we can use mesh currents, we can use really a lot of things. Every problem has its own design, if you want. So yeah, these are the two steps: find our Thevenin, and step 2, find V Thevenin using normal means. Okay, so here let's find our Thevenin first. So as we said and agreed, we replace the voltage source by a connecting wire, right? And then for the current source, we replace it by an open circuit. So imagine right here, roughly, there's an open circuit. This doesn't, yeah. Okay, here we have an open circuit, if you will. Like, there's no current that passes through here. So basically, we can ignore this line during our calculations. So apparently, if you want, let's draw it here, A, B, okay. So we have 6 ohms. Okay, there's nothing here because we short-circuited the voltage source, right? Here we have 3 ohm, the resistor. I suppose there's nothing down there. Yep. Open circuit here. So this is open circuit. I really there's really no point of drawing this because there's no current that flows in here. During our calculations, it doesn't really matter. So we have here 2 ohms, and then we have here, if I'm not mistaken, 8 ohms. Okay. And then back to B. So here we combine them as our equivalent from quiz 1. So we notice that these 2 resistors have the same node, really. So they are in parallel. We know that they are in parallel, so 6 and 3 combined, this is gonna give us 2, right? So here we're gonna have a resistor which is 2. And 2 and 2 in series combined, this is gonna be 4. And then we're gonna have 4 parallel with 8, which is gonna give us 8/3, right? So basically the way I went through it is 6 parallel with 3 give us 2, and then 2 plus 2, this is gonna give us 4. So the circuit looks like this, AB. This is 4, and this is 8. So then finally 4 parallel with 8, this is gonna give me 2.66 whatever. Okay, never ending. So it's clear from here that the answer is B, but I'm gonna go a step further and calculate Thevenin for practice purposes, right? Okay, so Thevenin. Now you can do mesh currents, node voltage, KCL, KVL. I'm gonna choose node voltage, obviously, because it's the easiest, right? Okay, so here we have, let's call this node right here. This is V0, okay? And this right here, now we can call this another variable like VA, but notice how from the ground up to VA we pass through this source. So this source is like +7. It pushed the voltage from the ground to VA by +7. So basically this node has a voltage +7 volt, because the only thing connected from this node to the ground is this 7 volt source. Okay, and finally let's call this node right here, I don't know, V1. Okay, and let's see the equations. We have let's say V0 minus 7 over 6 plus V0 over 3 minus 1, right? I'm calculating the current, so the current right here is V0 minus 3, V0 over 3, sorry. The current right here is V0 minus 7 divided by 6, so I went from V0 to 7, and I went by 6 ohm resistance, so V0 minus 7 over 6, minus 1, because this current source is giving minus 1 into the node, and then finally we have plus V0 minus V1 divided by 2, the resistance. This is all gonna be equal to 0. So this is equation 1. Equation 2, we're gonna apply KCL at V1. So here the current is 0, obviously, there's no current in here. The current in here is in different color. This is gonna be V1 minus V0 divided by 2, because I passed through a 2 ohm resistor. And then finally I have this current right here. I have this current down, which is V1 over 8. So plus V1 over 8 is equal to 0. So these are two equations, two unknowns in terms of V0 and V1. So you can solve them, and we get some values, right? We get some values, V0 and V1. Numbers from the calculators, obviously. Now what we can do to get Thevenin, notice how we only got V0 and V1, which isn't our target really. We really need Thevenin. So what we can do, we can apply a KVL that includes Thevenin. Now that I know all the voltages, I can simply just do a KVL with all these nodes that I found in order to find Thevenin. So one way to do this KVL is around the big loop. There is no other a really direct way to do this KVL. You could do this KVL right here, but it's really gonna be a lot of currents to deal with. Anyways, I'm gonna do it along the big loop. Okay, like this, like all around. So by this KVL we find -7. We start with -7, then hit plus Thevenin, right? And then down we find V1. So you could basically put plus V1. Or if you don't like this, you can put 8 into V1 over 8. So the current right here, because the current right here is V1 over 8, and then you multiply it by 8, which is back to V1. Right? If you don't see that the voltage at this node is plus V1, you could do the current multiplied by 8 ohm to find this voltage, right? Okay, this is all gonna be equal, sorry, wrong color. This is all gonna be equal to 0, so we find Thevenin is equal to 7 minus V1. And you're supposed to find the value of V1 from the calculator. From these two equations, this is equation 1, this is equation 2. You find the value of V1 from the two equations to unknowns, right? And this is gonna be a number, and after substituting, you're gonna find that Thevenin is equal to 4.11 volt, which is answer B. Okay, we're not done yet. They're asking us to draw the corresponding Norton equivalent circuit. So the Norton equivalent circuit. So let's see. We calculated Thevenin and Thevenin, so we can place these components like this. Thevenin, which is equal to 4.11 volt, and then this resistor right here, which is 2.67 ohms, right, like this. And this is terminal A, this is terminal B, right? So this circuit right here, if we were to connect anything between A and B, it really has the same effect as connecting A and B here by this same thing. So this entire circuit could be summarized by this drawing. So for Norton equivalent circuit, we apply the source transformation method. So source transformation tells you, so let me erase these right here. Okay, so we finished with this. Let me erase these here. So the source transformation method tells you that, suppose right here I have like plus minus V into R, like this. This becomes a current shooting upwards, so it shoots with the same direction from minus to plus, so it points upwards. Not really upwards, but from the minus terminal to the plus terminal of the voltage source. The value of this current will be V over R, the value of this current source, and we place the resistor in parallel. So this is R, and these are the two terminals. The resistor is in parallel, and obviously if I want to go from this back to this, I can, obviously. The current source I multiplied by R, it becomes a voltage source, negative terminal from the back of the arrow, so it's gonna be a minus here and plus at the tip of the arrow, right? So I'm back to V, and the resistor, instead of making it in parallel with this source, I make it in series. So basically finding the Norton equivalent circuit is applying this source transformation. So in here, what I can do is draw a current like this from minus to plus. Its value is gonna be, the value of this current is gonna be I Norton, which is the voltage divided by the resistance I got, which is 2.67. We find 1 point, which is 1.54 amperes. Okay, and then we keep the resistor as is. This resistor is gonna have a value 2.67, like this. Okay, this right here is Norton, the Norton equivalent circuit. So we just applied source transformation. The whole idea of source transformation is that if we have a voltage and a resistor in series with this voltage source, we can transform it into a current source and the resistor in parallel. This may simplify some calculations, but this is mainly used for Thevenin circuits, transforming them from Thevenin to Norton equivalent circuits. Okay, so the answer right here is answer B, and we drew the Norton circuit right here. Okay, so for problem 2, we have this circuit. Now, if we remember, we discussed that Thevenin circuits have 3 cases. Case 1 was that we have all independent sources, but here we don't have all independent sources. This is independent, okay, but this is dependent, which is a problem. This is a dependent source, which is a problem. Yep. Okay. So let's discuss case 2. So here we have independent plus dependent sources. We have both sources. So step 1, find Thevenin. Okay, now obviously when I say find Thevenin, we assume that the terminals where I find Thevenin are open circuited, so no currents flow through this open circuit. No current flows through Thevenin. So we find it by the usual means, right? I'm gonna say this: assume open circuit. Assume this is open circuit. So you can find it by the usual means, like node voltage, mesh currents, KCL, KVL, anything really works. Source transformation, even if that makes your life simpler. Step 2. Short circuit your terminals and find I short circuit. So the idea behind this is that now that you found Thevenin after assuming an open circuit across the terminals, now you short these terminals, so there's gonna be a connecting wire and there is a current flowing in there, and your job in step 2 is to find I short circuit, is to find the current flowing in this short circuit. And you can also apply all the usual means. Notice there's no deactivation of sources. The only time you deactivate sources is in case 1, if all the sources are independent. So let's say you found I short circuit. Step 3 is to calculate I Thevenin. So I Thevenin is simply gonna be Thevenin divided by I short circuit. So notice how we start by finding Thevenin, then we find I short circuit and then R Thevenin. So R Thevenin comes after Thevenin. So there's like some procedures we must follow in order. Really, case 1, there isn't this ordered procedure. You can really find Thevenin before R Thevenin and nothing changes, right? But here I need Thevenin and I short circuit before I actually calculate R Thevenin. So let's go back and apply what we have learned here. So first of all, I need to find Thevenin, right? And I assume open circuit. So the current right here is 0. I equals 0 amperes. So let's see how can I find this. I'm gonna apply mesh currents. This sounds appealing. Why? Because the current right here is 6, which is exactly this value. This is 6 amperes. So I know this current. I really don't need to do a mesh equation in this mesh that I know. Here on the other hand, I'm gonna call it IA, and here I'm gonna call it I delta. Now why did I call it I delta? Because of this current right here. The current right here is 0, so this doesn't change on the value of I delta. I delta is still gonna be I delta. It's not affected by this current in here. So I'm gonna call this mesh I delta for simplicity. Okay. Okay, now let's do the equations. Let's do the equations. So we have in mesh of IA, we're gonna have 2 into IA, we're going with the direction of IA, minus 6 from above, and then plus 4 into IA minus I delta, and then I hit this voltage source, this dependent source, which has a value of 4 I delta. All is equal to 0. Now for equation 2, I'm gonna apply mesh, the KVL, the mesh in I delta. So we have 4 I delta minus IA. So notice how I delta flows into the 4 ohm resistor, but IA flows in the opposite direction. So this is gonna be I delta minus IA if I go with the KVL like this. Now I delta, and we have plus 5 I delta minus 6, again by the sign convention, and then finally we have 1 I delta, so just I delta. Okay, now again, two equations to unknowns, you plug it into your calculator. This is going to be equation 1 and this is going to be equation 2. Plug it in your calculator and now you're going to find the values of IA is going to be equal to something and I delta, which is going to be equal to something. Now I found I delta, IA and all of these. We are ready to find Thevenin. Now, how would you do Thevenin? You can say, now, you can see that Thevenin, the terminals A and B are in parallel here. So this is also A, this is also B. So the voltage from here to here is also the voltage from here to here. A and B are parallel with this 1 ohm resistor. So the voltage Thevenin, let me go to here. Thevenin is gonna be equal to 1 I delta, Ohm's law. So Thevenin is exactly equal to I delta, and in this case, we're gonna find I delta to be 3.8. So the answer is right here. A. Thevenin is 3.8. Okay. Again, you found I delta IA, and then you notice that Thevenin is the same as the voltage across this 1 ohm resistor here, and the voltage across this resistor is exactly 1 times I delta. So I delta, and you found Thevenin. Now I need to find I Thevenin. Right? I need to find I Thevenin. So okay, I found all of these. Now I Thevenin. And let me erase these right here. I Thevenin, we decided that we need to short circuit the open terminals. So we do a short circuit right here. And current is allowed to flow right here. So I'm gonna call it I short circuit. Okay. Current is allowed to pass through here, and I need to calculate this current. Now, before I do anything, I can simplify the circuit. Now that I have a short circuit, I can simplify everything. So I noticed that this 1 ohm resistor is shorted by A and B because the voltage here is 0 volt, a connecting wire. So the voltage in here is also 0 volt. So this is basically useless. Like, this is useless. Another way to think about it is that if I have a current right here, let's call it I, and let's say it goes into here. Now, would it prefer to go through a resistive branch or a free branch? Remember, current flows through the branch of least resistance, so of course, all of the current is gonna go through the branch of AB, this short circuit. So, the 1 ohm resistor is shorted, and I can simply ignore it. Like, it doesn't even exist. Nothing is here. Because no voltage drop across the resistor and there is no current. So this doesn't exist. Now what can I do more? I said I let this branch, basically this branch has 0 volts and 0 current by what we have discussed previously, but the current right here is I delta. Right, and I suppose that I delta is equal to 0. Not supposed, but argued that I delta is equal to 0. Now, if I delta equal to 0, look at this voltage source in here. It's for I delta, but I delta is equal to 0, so this is equal to 0. And if this is equal to 0, I can also ignore this. I can assume it's a short circuit. Okay. So we have discussed all of this. And we have seen that I delta is equal to 0. So basically what we have, the image, is that I have 6 amperes in here. I have some other unknown current IA in here. Notice that we have a short circuit in the place of the dependent source, and I have a big current in here, which is I short circuit, which also extends to the other side like this. So this entire loop is just one mesh. There isn't anything that exists in the middle, because we argued that the 1 ohm resistor does not have a current passing through it, and therefore no voltage. Okay, so we can apply the mesh currents in here. So the equations are gonna be sorry, not IA. So we're gonna start with the 2 ohm resistor, which is gonna be 2 into IA minus 6 plus 4 into IA minus I short circuit. Again, you can verify this. We took all the directions into account. This is gonna be equal to 0. And then we do the mesh in I short circuit. So 4 I short circuit minus IA plus 5 into I short circuit minus 6. Minus 6. This is all gonna be equal to 0. Now we have equation 1, equation 2. And again, you're gonna solve it. You're gonna find I short circuit and you're gonna find IA. But something interesting, you're gonna find I short circuit to be 6 amperes. Which is strange, because the 6 amperes in here, it's like this 6 ampere, it's entirely flowing into here and not in here. Or when it comes back in here, it doesn't flow back in there. It continues like this. Now, I want to argue why this result is acceptable. It's because now the 6 amperes goes from here, right? It's gonna see a resistive load or nothing, because this doesn't exist, because I short-circuited the thing. So it's gonna see nothing. The current right here is 0 amperes. Nothing flows into here. It's gonna prefer going like this. Now it reaches here, and again it sees nothing. Remember this, we have cancelled it because I delta in here is 0 amperes. So this is a short circuit. So here it's gonna see nothing, but here it's gonna see a resistive load. So again, the current right here is 0 amperes, and it's gonna keep going. Now again, I'm here. Would I rather go back into the source or go through this resistive path? Again, I'd rather go back to the source. Like here, there's a short circuit, and I went back to my source. So the current right here is 0 amperes. Nothing flows into here. So the general image is that this 6 ampere source, it goes like this and back to this. And if I had a short circuit right here, this current right here is gonna be exactly 6 amperes. Nothing flows into here, nothing flows into here, nothing. See? The simplification, the idea, or the permission to have a short circuit across A and B have basically solved the entire circuit. After we did the mesh currents, obviously, but this short circuit is grace, right? Okay. So we found I short circuit, which is equal to 6 amperes now. The rest is easy. We find I Thevenin, which is equal to V Thevenin over I short circuit. And V Thevenin, we have calculated it to be 3.8, which is I delta from the previous example, and I short circuit is gonna be 6. And if you do the ratio, it's gonna be 0.633 whatever. So equal to 0.633 ohms. It goes on. So the answer is A. Okay, so we have discussed case 1 and case 2. Now we have case 3, which is all dependent sources. There are no independent sources. There's nothing that drives the circuit. Okay, before I go back to the notes up there and discuss case 3, I need to ask, what is Thevenin? Right away, you can guess Thevenin right away. So the argument is that the entire circuit doesn't have any independent source. So there's no source of energy without dependence on another thing. While in here, we have this dependent source, for example, it depends on Vx. But Vx doesn't really have a source. Again, this source right here is dependent on what Vx is, but Vx has really no origin. It really isn't driven by an independent source. So if you don't have an independent source in here, basically there's no energy in the circuit. There's nothing to supply energy to the circuit. So Thevenin is 0. I don't have an independent source to supply me energy without depending on another variable in the circuit. So immediately Thevenin is equal to 0. This I can guess immediately. So I'm gonna go back to my notes, and for case 3, I'm gonna say all sources are dependent. So for step 1, which is the easiest step, Thevenin is equal to 0. 3 points, right? Step 2, I apply injection method. Now the name is gonna be strange. What is injection method? Injection method is when we place a voltage source across the terminal of interest, or a current source, really, it doesn't really matter. And if I place a voltage source, I measure the current, right? So I'm gonna say in step 2, here's like a barrier. Step 2, place Vt, a source, across terminals, okay, and measure It. Okay, so I placed a voltage source across the nodes, across the terminals, and this voltage source causes a current to flow out of it, and this current is It. The final step, step 3, is just R Thevenin is equal to Vt over It. Okay, let's carry this and apply it here. So I'm gonna place a voltage source plus minus from here to here. Now you can call this source Vt. You can call it Vt and solve the circuit in terms of Vt, but really you're gonna end up with equations with an unknown Vt, which really isn't a number that we're comfortable with. We can't put Vt into a calculator, right? So what is advised to do is that you pick a number. Pick a random number. So this number can be 1 volt, it can be 5 volt, it can be 12 volt. I'm gonna go with 12 volt. So now you're gonna ask, if I choose a number but another person chooses another number, won't we get different answers? And the answer to that is no, because depending on the value of Vt, It will differ. And it will differ in such a way that Vt over It is gonna be constant. So you can choose any number you want for Vt, and as long as you carry the operations without mistakes, you're gonna get the correct answer. So here's It. I don't know It, I need to calculate it. But I know Vt. I assume it to be 12 volts, which is a correct thing to do. You can assume Vt to be 12 volt, which makes your calculations easier. Okay, so in order to find It, I can use well, actually, let's see if I could use node voltage. Okay, like this. Now the value of the voltage in here is 12 volts, right? Because why? Because from the ground up to this node, I only have this 12 volt source. So it's like the only thing that I'm connecting between this node and the ground is a 12 volt source. So this node is necessarily 12 volts. Now this entire thing is one node because notice we have node A, connecting wire, this is the same node, connecting wire, this is the same node. So everything is the same. Now let's do nodal here, or KCL actually. So we need the current in here, which is 12 minus 100 IX divided by 50. And then I have plus Vx over 50. But notice how Vx is 50 Ix. By Ohm's relation in here, we find Vx is equal to 50 Ix. So I can do plus 50 Ix divided by 50. Cancel, which is gonna be Ix. And then we have plus Ix. This is the current right here. And plus Ix, which is the current right here. So plus Ix. And finally I have minus IT, which is the current flowing like this, minus IT. Okay. Now, okay, this is all gonna be equal to 0. Now, what we can do is that, you notice, this we could simplify this into 12 over 50 minus 2Ix, which is this minus 2Ix, plus Ix, plus Ix, minus IT. This is all gonna be equal to 0, right? So notice here we have minus 2Ix, plus Ix, plus Ix, so I can cancel. And we're left with IT is equal to 12 over 50 amps. Okay, now we found IT and we said that R Thevenin is gonna be equal to VT divided by IT. So we're gonna have VT is equal to 12, IT is 12 over 50, so 12 and 12 cancel, carry the 50 upwards, so we have R Thevenin is equal to 50 ohms, which is answer B. Okay, so if I had to draw the equivalent circuit, suppose that the question was to draw the equivalent circuit of problem 3, which is all independent sources. Remember, VT doesn't exist. It only exists to test. It's an injection method. So I created it. The equivalent circuit of this is really gonna be this. It's really just a resistor. This entire circuit is really nothing but a resistor, which is R Thevenin. Okay, these are the cases for R Thevenin. They're not difficult. There's 3 cases, and these cases are really simple. You just need to practice. So I covered an example for every case for the first 3 problems. So in problem 4, they're asking what is the value of RL, this in here, that would allow for maximum power transfer to RL. So what is the value of this resistor so that I get the maximum power across this resistor? So if you know from Thevenin, we know that if I have if I have a really big circuit, there's really resistors and stuff, okay, I can simplify this into V Thevenin and I Thevenin. And the idea behind RL receiving the maximum power, so if I connected RL in here, this is equivalent to connecting RL across this open circuit, because here we have terminals A and B, also we have here terminals A and B. So if I connect RL across A and B, we also connected in the Thevenin equivalent circuit. So the idea is for RL to have maximum power, RL needs to be equal to V Thevenin. RL equal to RL is equal to R Thevenin. This is gonna guarantee maximum. This is gonna guarantee maximum power transfer. So there's a derivation for this. So basically it's gonna be, you're gonna say that power is voltage times current. The expression of voltage is given by voltage divider, so V Thevenin into RL over R Thevenin plus RL. The current is given by Ohm's law, which is also a function of the voltage, and For it to be maximum, you take the derivative, set it equal to 0, and after solving a lot of things, you're gonna find RL is equal to R Thevenin. You're not asked about the derivation. You're asked only about the final result. RL is equal to R Thevenin. So to find the value of RL, we need R Thevenin. We don't need V Thevenin in the case that we don't have dependent sources. So let's see here. I have an independent source, and I have this source here, independent source. I don't have a dependent source. I don't have this, which is amazing because I can deactivate the sources and find R equivalent, which is exactly R Thevenin. Okay, so I'm gonna do this. I'm gonna deactivate this voltage source right here. So deactivating it is gonna be a connecting wire, and we deactivate this 2 ampere source. Deactivated. So if we deactivate this 2 ampere source, this is gonna be an open circuit. So nothing exists in here. There's nothing in here. And if I short circuit in here, I notice that the 3 ohm and 6 ohm are in parallel. So if I had to draw the circuit, it's gonna be like this. It's gonna be 10 ohm, and I have 3 ohm, and then in here 6, 3, and I need to find R equivalent as seen from here, as seen from the terminals of RL. So how do I do this? It's simple. R equivalent. What's R equivalent in here? So it's 10 in series with 3 in series with 6 parallel with 3. So these two are 6 in parallel with 3. Do the calculations. You're gonna find. Well, actually, yeah. Let me do it. 10 plus 3 plus 6 times 3 over 6 plus 3. We're gonna find 15. So R Thevenin is equal to 15. But for maximum power transfer, this should be equal to RL. So RL is also 15. This is for maximum power transfer. Okay. Okay, so in problem 5, we have for the circuit above, determine the current I0 due to the effect of IS equals 3 ampere only. Okay, this is an example of superposition, right? So in superposition, we consider the effect of one source, deactivate the others, then deactivate the source and consider another source, so on and so forth, and then all the answers are added up to find a total value. But here we're asked for the circuit above, determine the current I0 due to the effect of IS only. So due to the effect of this only. So this 20 volt is not needed, and if I don't need it, I deactivate it. Deactivate it. So connecting wire. And I don't need this, connecting wire. And I don't need this, open circuit. This doesn't exist. Okay. Let's redraw the circuit. Let's redraw this. So I'm gonna have a current source in the middle. This is gonna be 3 amperes. And I have 80 in series with 80. This is connecting, whatever. So 80 series with 80 is gonna be 160. Okay. And then this here doesn't exist, so I'm gonna do 100 ohms like this, 100 ohms, and then 80. I'm just copying the figure, okay? After the edits, after deactivating the sources and whatever. So this is the shape of the circuit we have. So obviously we have 80 and 80, which is 40. And 40 and 100, which is 140. So the circuit simplifies to this, simplifies to 3A, 160, and then 140. Now, does this remind you of something? We have a current source giving current 3 amperes, and it's divided between this branch and this branch, which is current divider, two resistors in parallel with the current source, current divider. So I need to find I0. Remember, I need to find I0, which is the current flowing through the 100 ohm resistor, and the 100 we had 40 in here after combining this and this. So is the current passing through this branch? This is I0, so this is I0. Now, how do I get I0 by current divider? Simple. We say that I0 is equal to the total, which is my source, this is my source, multiplied by the addition, which is 160 plus 140. And for the numerator, I choose the resistor that I'm not operating on. So if I'm operating on 140, I need the I0 across I40. I choose the 160. And this value right here is gonna be 1.6, if I'm not mistaken. So we have 3 over 300, yep, times 160. So 160 over 100, so this is going to be 1.6. So the answer is 1.6. So here it's an example of source transformation, not source transformation, of superposition, where we consider the effect of one singular source and we deactivate all the other sources that I don't need, and I find my value. And if the problem was complete, if it was to find all the currents in 100 ohm resistor, if I need to find the effect of everything, I deactivate I0 and then reactivate this, and then I deactivate this and reactivate this, for example, and so on and so forth. I get a bunch of values just like I did, and then for the total effect I add addition of these values. Okay. Problem 6, operational amplifiers. So operational amplifiers are really interesting because first of all, let's see what's the benefit of having an operational amplifier. So the idea of having an operational amplifier is that if I feed it a voltage, if I give it a voltage, let's say here VP, VN, whatever, it's gonna do an operation in here, which is essentially VP minus VN. Okay, and it's gonna multiply it by something, call it A. So I multiply my output, I multiply my input, sorry, and it gives me an output. So here I have a VO. So I put an amplifier to amplify my voltage, to give it an input, multiply it, amplify it, and give me an output. This is the point of an amplifier. Now, amplifiers also have, let's say these terminals, okay? And here I have plus VCC, and here I have minus VCC. So, amplifiers in most circuits look like this. So this is the positive input, positive in. This is the negative in. Now for EECE210, for our course, plus and minus really don't matter, because of a simple formula we're gonna discuss later. But plus VCC and minus VCC do matter, because the operation of the amplifier looks like this. Sorry, it looks like this. So I have some ground in here I must not pass, so like this. And then I operate in a linear region, and then I go back to some value I cannot pass. This value is plus VCC, and this value is minus VCC. So the regions from here and onwards, and the region from here and onwards, are called saturation. Now, what do I mean by saturation? It's like if I find a V output, if I find an output voltage which is greater than plus VCC or less than minus VCC, I say the op amp or the amplifier is saturated, and whatever value I get, I cap it down to minus VCC or plus VCC. So let's say, for example, I have an amplifier that looks like this, plus 15 and minus 15, and I found a voltage in here which is minus 20. Well, minus 20 is less than minus 15, so I have this minus 15 and plus 15. Minus 20 is over here, below minus 15, so I say the operation amplifier is saturated. It's operating beyond its boundaries, so minus 20 is illegal in this case. It's an illegal value, so what I do is get it back into minus 15. Same case if I calculated plus 20. If I calculated plus 20 in here, I'm gonna say the operation amplifier is saturated and I get this value back to plus 15. Okay. This is about saturation, and one last remark is that the region in here, I have freedom, so whatever I get for V out, if it's between minus VCC and plus VCC, I'm gonna call it linear mode or linear region of operation. Whatever I get for V out, I'm totally okay with it. There's no saturation, I'm in linear mode. It's totally legal. Okay. This is for regions of operation for the amplifier and the concept of what is an amplifier. Why do I really include amplifiers into my circuits? Now for how to deal with amplifiers in any circuit. So I'm gonna work on this amplifier as an example. This amplifier has two inputs, right? Plus N and minus N. So I'm gonna call them VP and VN. V positive and V negative. And I have here V0, which is output. So in this example, VO is also here, which is also in here. V output. This is my output voltage. I feed my amplifier something and I get an output. Okay. But I also have another thing. I have the currents flowing into the amplifier. I have this current right here, which is, I'm going to call it IN. And the current flowing in here, which I'm called IP. So amplifier looks like this. I'm gonna ignore linear region. I'm gonna say plus VCC. I'm gonna ignore saturation. So I'm operating in linear region. Okay, V0. Like this. The value of this voltage right here is VP. The value of this voltage right here is VN. I have a current entering the op amp, which is IP. Current entering the op amp, which is IN. But the catch is, in EECE210 and operational amplifiers in specific, we're gonna have two rules. Number one, VP is equal to VN. It's sorry, not VN, VN. It's always the case. VP is equal to VN, so this point is equal to this point. They have the same voltage. Second rule is that IP is equal to IN is equal to 0. No current flows into the op amp. فيكم تتخيلوا كأنه إذا فوت current بحرقه للأوب amp. It's not really the case, بس إنه I can't push current into the op amp. It's internally the op amp looks like an open circuit. So an open circuit, I can't ever have current flowing through an open circuit, right? So these are the rules really. The voltage across the inputs, the voltage across the first input is equal to the voltage across the second input, and the current, I can't have current flowing into the operational amplifier. And I'm gonna work with this. Now, as a side note, which is really not technical, but most, and I'm gonna say 99% of op-amp problems are really just node voltage in disguise. So, whenever I see an operational amplifier, I'm gonna just name a whole bunch of nodes and apply KCL everywhere. So, node voltage. I like node voltage with operational amplifiers. So let's see. Here I have Vn, which is equal to this, which is equal to this. So this right here is Vn. And I have in here Vp. Now I have this 10 kilo ohm resistor, which is causing me problems. But remember, the current right here is 0 amperes. So the voltage across the 10 kilo ohm resistor is 0. And if the voltage is 0, it's a connecting wire. It's like it never existed in the first place. So this right here is a short circuit, and VP carries on to be here. And we have discussed that VP is equal to Vn. So whatever I find in Vn is gonna be equal to VP, and whatever I find in VP is gonna be equal to Vn. So now you ask yourself, what's easier? Is it easier for me to find Is it easier for me to find Vn first or to find Vp first? Well, if I'm gonna consider Vn, I have this known to be Vout, which is this. Now, if I do a KCL across Vn, it's gonna be problematic because I start with my output, which is really something I really don't want. I need to calculate my output. I really don't need my output to be in my first step, so maybe it's easier for me to start with Vp instead of Vn. So yeah, let's start with Vp. So Vp, again, I have no current in here, I equal 0, so the circuit across the circuit including Vp looks like this. It looks like plus minus 3 volts, 10 kilo ohms, and then another 10 kilo ohms, and my Vp is here, so, and I have a ground in here, so my Vp is plus minus Vp across this 10 kilo ohm resistor. Now, why did I do a branch like this? Because current right here is 0. I equal 0. So this branch doesn't even exist, so I can neglect it. This is a connecting wire. And it goes to nowhere. The current is 0. Yeah, the current is 0, so like there's an open circuit in here. Current can pass through here, so I can ignore this. Okay? So my circuit does look like this, and this is a voltage divider, right? Because I have two resistors in series, 10 kilo ohm and 10 kilo ohm, and they're in series with the voltage source. So, and notice how the resistors are equal. So if I'm gonna do Vp, the voltage divider formula is 10 over 10 plus 10, which is equal to 3 divided by half. Each resistor gets equal voltage. I divide each voltage by half for the resistor, I get 1.5 volts. So Vp is 1.5 volts from my analysis. So this in here is 1.5 volt. Now I can transfer this into here. This also is 1.5 volt because Vp is equal to Vn. Vn is equal to Vp. So Vn is 1.5. Now I can do a KCL. Erase all these, and I can do a KCL. I can consider the current flowing like this, the current flowing like this, but remember the current flowing like this is 0 amperes. No current flows into the operation amplifiers, and I can see the current in here, so this is V out. Okay? Okay. So the game with operation amplifiers is to apply node voltage, and I'm gonna do precisely this right here. So we have Vn divided by 25k. Remember, the k is really important, don't forget it, which is 10 power 3. So when I say 25k, I'm really saying 25 times 10 to the 3. Okay? So plus 0. So I'm gonna leave it out, no current flows into the operation amplifier, plus Vn minus V out over 175k is equal to 0. But I know the value of Vn previously from Vp. I calculate Vn from Vp, so I'm gonna say 1.5 divided by 25 times 10 to the 3 plus 1.5 minus V out. I need to find the value of V out over 175 times 10 to the 3. This is gonna be equal to 0. One equation, one unknown. Basically, it's simple. So V out is gonna be 6. It's gonna be 12. I'm sorry. So if you do the calculations, you're gonna find that V0 is gonna be equal to 12. So get this to the other side. Get this to the other side multiplied by whatever, and you're golden. You do whatever you want. It's a single equation, single unknown. So V out is equal to 12. Anyways, problem 7, which is really interesting. It's about saturation. Okay. Which of the following operation amplifiers are saturated? And here we notice that we have two operation amplifiers in the same circuit. And this is really simple. You're gonna see that this is really simple. And I have in here, you're gonna start calling nodes, right? We have already here, we have VO1, which is the output of the first operation amplifier. We have VO2, which is the output of the second operation amplifier. And I'm gonna put VN1 and VN2. Now, sorry, no, VP1. So VN1 and VP1. So, sorry. What is easier for me really? Is it easier for me to deal with VN1 or VP1? Now, if I deal with VN1 and do a KCL, I'm gonna meet VO1, and I really don't want my output to show up in my first equation, so I start with VP1. Okay, so starting with VP1, we find plus 10 volt. So if you want, you can imagine a voltage source right here, plus 10 volt, 4 ohms and 4 ohms, and then like this, and I have VP1 in here. Now you're gonna ask me, but 4 and 4 are not in, they're not in series because there's this branch in here, but this branch in here has current equal to 0, and current equal to 0 means open circuit, so I can forget it. Well, the current in here and the current in here also, so I can consider these in series. So again, by voltage divider, VP1 is gonna be equal to 10 times 4 over 4 plus 4, which is 10 divided by half, which is 5. Okay, VP1 is equal to 5, so I carry this value, this is 5 volt, I put it in here. So the circuit, here we have plus 5, and here we have also plus 5, they're equal. So now I can do a KCL here. Okay, I can do a KCL in there. So let's do this KCL. So we have 5 minus 12 divided by 4, the current in here, plus the current in here, it's 0, no current flows into the op amp, plus 5 minus VO1 over 4T is equal to 0. Now if you do the calculations, you're gonna find that VO1 is equal to minus 65. Okay, VO1 is minus 65 volts, because this is one equation, one unknown, and if you plug it on the calculator, you're gonna find VO1 is equal to minus 65. But remember, the question is about saturation. Which of the following are saturated? So after I find my value in here, which is minus 65 volt, I need to check with the boundaries of my operation amplifier, which is minus 12 and plus 12. So I look at minus 65 and I think to myself, is it greater than plus 12? No. Is minus 65 less than minus 12? Yes. Minus 65 is less than one of my boundaries, so the operation amplifier is saturated. So one saturation. I've reached saturation, and I found minus 65, but the op amp is saturated. So is it legal for me to have minus 65 volt? I'm asking too much from the operation amplifier. Like the limit of the op amp is 12, but I'm asking it for 65, which is impossible. So the value I calculated in here, which is minus 65, I'm gonna roll it back into minus 12. So minus 12. But I know deep down in my heart that the first op amp is saturated. So I have saturated. So I know for a fact that my answer is either this or this. Okay, so this is minus 65, which I roll back into minus 12, and let me erase all of this. Yeah. Okay, so I find here minus 65, which I'm gonna quickly put it minus 12, and 1 is saturated. Now let's calculate for op amp 2. Now, the starting point of any op amp problem is to mark its nodes. So here we have VP and here we have VN. Now, immediately you can say VP is equal to 4 volt. VP is equal to plus 4. It's immediate. I have a source in here and it's directly connected to this node, so VP is equal to 4. So Vp is equal to Vn, and Vn is equal to 4. Now this Vn is equal to 4 volts. See, I work on one terminal of the op-amp and I transfer what I find into the other terminal. So I find here Vn, which is equal to 4 volts. And let's call this node, for example, let's call this node VA. So remember, our objective is to really apply node voltage whenever we can, and don't be scared to label nodes if you don't know. If it's unknown, you can label it, and you can find another equation later for it to be included in a KCL later, right? And I know here it's 4 volt. I need to calculate for VO2. Okay, and here we have VA, right? Okay. But notice something about VA. The current, look at the current in here. The current in here is 0. Why? Because no current flows into the operational amplifier. So in fact, my VA is actually the same as Vn. It's like if no current passes through the 3 ohm resistor, I can short. No current. So this Vn, put it in here, which is equal to 4 volts. Okay, this all because I equals 0, which enters the operational amplifier. So back to here. I need to find VO2. Remember, I have plus 4 volt here, and I need to find this. So I can apply KCL in here. I can apply node voltage. So the current in here is 4/3. The current in here is 0. No current flows into the operational amplifier. And then finally plus 4 minus VO2/3. The current in here. All equal to 0. Now, I can do all my so basically we have this KCL in here, so you can find the value of VO2, and after calculation, one equation, one unknown, you find VO2. So in here VO2, which is equal to 8 volt. And now that you got an output for the second operational amplifier, now that you have VO2 in here, which is equal to 8 volt, and the question asks you what is the state of the operational amplifier in terms of saturation and whatnot, and you find 8 volt, you're gonna compare this value with plus 6 and minus 6. Is 8 less than minus 6? No. But is 8 greater than 6? Yes. So if I think about it in terms of regions, the image is like this. This is plus 6 and this is minus 6. So whatever value I find in here, put it back into minus 6. And whatever value I find it in here, put it back into plus 6. This right here is a linear region. So whatever value I get in here is okay, because it's between 6 and minus 6. But here I found 8, which means that the operational amplifier is in saturation, and because it's in saturation, it can't provide any more output, it can't provide any more voltage. So if I found 8, it's impossible, it's illegal. So I put it back into 6. So actually this 8 volt is 6. If I had any more circuit to deal with, for any intent and purpose, I can consider VO2 to be 6. And because I needed to do this clipping, because 8 is greater than 6, I say that 2 is also saturated. So I have 1 is saturated and 2 is saturated. So both are saturated. Answer D. Okay. This problem is very important, Actually, no, they put it like this, very important, right? Okay, so I have 2 operational amplifier and the circuit looks big. Okay, the circuit looks big, and the thing is that I have this connecting wire in here which is taking some input, and placing it directly out the output. And you can think of it the other way around. I have some output and I get back in here and place it as the input. So there's something tricky. I have this direct relation with the input and the output and the indirect relation between them. So anyways, this is like the really tricky part about this exercise. So I'm gonna start at the first operation amplifier in here, VO1. VO1. So I'm gonna call this VO1 as the output of the first operation amplifier. Now I start with the inputs, which are in here VP and in here VN, the inputs of the op-amp. Now, what is easier for me? Is it easier to start with VN? But if I start with VN and I do a KCL, I'm gonna meet with VO1, which is not really suitable for first equation. So I'm gonna start with VP. Now, what's VP? Is VP equal to 0? Is VP equal to 8? Well, which one of these? It's actually none. VP is neither 0 nor 8 volt. So think about this. Think about it this way. It's like VP is not 0 because I have current that comes from the ground. And yes, current can come from the ground. The ground really symbolizes that I connect the circuit to a 0 potential reference, but I really can have -2 volt. Like this is a ground, but I can have beneath the ground, which is not shown, a -2 volt. So I drag current. So really it's totally legal to have current flowing out of the ground. So I have a current in here, and if I have a current in here, I have a voltage drop across the 4 ohm resistor. So VP can be 0, and VP can be 8. VP can be 8 because it's really not like this circuit. It's really not like I'm saying this. Like this configuration in here and this configuration these are not equal. If it was the first one, if it was this, I'm okay. VP is equal to 8 indeed, but this is not the configuration I have. VP is connected to some other node in here, and before that it passes through the 8 volt. So my job is to find this. What is this? So let's trace it. Let's trace it. I'm in here. I go back. I found this VO. So VO is this node, which is connecting wire this node, and the same as this node, the same as this node. So V out actually goes all the way into here. So this node is VO. And then what about VP? I found this to be VO. What about VP? So if you wanna draw the circuit, it's gonna be like this. I have a ground. I saw VO, and then plus minus 8 volt, and then VP, and then ground. So minus plus VO, and then minus plus VP. So if I do a KVL, I'm gonna find minus VO plus 8. So minus VO plus 8 plus VP. This equal to 0. So VP is equal to VO minus 8. Okay. So VP is equal to VO minus 8. It's not 0, it's not 8, it's VO minus 8. VO minus 8. And I did all this calculation, and I found VP across the first operation amplifier. So I can go ahead and say VP is equal to VN, and I say that VN is also equal to VO minus 8. Okay. Now I do a KCL on VN. The KCL is ready. So the current in here is 0, and the current in here, it's 0 because no current flows into the op-amp. So VN minus VO divided by 1K, so 10 to the 3, don't forget it. 0 I don't include it. And so let me replace directly. So instead of VN, I'm gonna replace it directly with VO minus 8, and then VN minus VO1, VN which is VO minus 8, minus VO1 over 2k, all of this equal to 0. So I have two equations, I have two unknowns, one equation, so I can get VO1 in terms of VO. How do I do this? I do some simplification, so I multiply everything by 2k, this and this cancel, so I multiply all of this by times 2k, I get 16 minus 16 plus VO minus 8 minus VO1 equal to 0, so this and this, this and this minus 24, get it to the other side, this flip sign, whatever, so VO1 is VO minus 24. So VO1, this is VO minus 24 after my KCL. So far, most, like 99% of op-amp problems are really just node analysis. So far, okay? So VO1 is VO minus 24, and I can carry this node in here, VO1. Now back to my problem. I start with the second operation amplifier. I entered the territory of the second operation amplifier. So I'm gonna say this is Vn, and this here is Vp. And is Vp equal to 0? No. Is Vp equal to VO1? No. Well, the way I can proceed with this is that I do a KCL across Vp. So let's do this. So a KCL on node Vp, so we have Vp over 1k plus Vp minus VO1 over 2k plus 0, nothing enters in here, this is gonna be equal to 0, and multiply everything by 2k, so 2Vp plus Vp minus VO1, but VO1 is VO minus 24, so plus 24 minus VO1 equal to 0. Sorry, not VO1, it's VO. So VO1 is this. So Vp, this is gonna be equal to VO minus 24 over 3. And I carry this Vp up onto Vn. And I found Vp, so Vn is equal to Vp is equal to VO minus 24 over 3. And since I found Vn in here, I can do KCL simply. Now, I can do KCL because Vn now is in terms of VO, and VO1 is also in terms of VO, and I have VO in here, so everything is ready. I can do a final KCL and finish the problem. So let's do exactly that. So I'm gonna leave this result down there, and let's proceed. So we have the KCL is Vn minus VO1 divided by 2k plus 0, nothing, enters op-amp, Vn minus VO divided by 4k, this is all equal to 0. Now, the expression of Vn is VO minus 24 over 3, VO1 is, well, VO1 is VO minus 24, flip its sign, 24, plus 24 and, sorry, plus 24 and minus VO, all of this divided by 2k, and then VO minus 24 over 3 minus VO, all of it 4k, all of this is equal to 0, right? And then this thing only contains VO, some equation in terms of VO. And if you solve this equation, simplify the equation, put it in your calculator, whatever, it's one equation, one unknown, you find VO is equal to 12 volts. So the answer in here is 12 volts. So now, recap of what we did. We started with the first operation amplifier, we designated Vn and Vp, and we considered Vp in terms of VO, considered this relation, and then after this, we got Vp in terms of VO. So Vn is equal to Vp, which is in terms of VO. Do a KCL to find the output of the first op-amp, which is also in terms of VO because of Vn. Now, go to the second operation amplifier, do the same things with Vp and Vn on the second operation amplifier. So they're gonna be in terms of VO1, which is in turn has terms VO, right? And then one final KCL across Vn gets you one equation that relates everything in terms of VO. So this problem is considered really difficult, really, and so far it showed up in two previouses. Okay, so this problem showed up in two previouses, and the values are different, obviously, but the idea is the same. Is that I connect a wire from here up to the output. But the idea still stands. Operation amplifier is all about node voltages, and not being afraid if I don't know a node, I quit the problem. No, if you don't know a node, you can call the node something and apply KCL on it. So anyways, in problem 9, which is the last thing on operation amplifiers, I think, yep. Problem 9, the operation amplifiers are operating in linear region, so there is no saturation. Determine VO. Okay, so I'm gonna work with the first operation amplifier. So here's VP, here's VN. So I'm gonna carry VN here, and I'm gonna carry VP down here. Now, this is easy. VP is equal to 0 because it's directly equal to the ground. These nodes are the same, so VP and ground are the same. VP is 0. So I'm gonna transfer this to VN. VP equal to 0 and VN is also equal to 0. Now, this right here, VP is equal to 0, but notice something interesting. If the difference from here to here is 0, it's like this source and the 2k ohm resistor did nothing. This branch in here did nothing. Like, the voltage I got from the 0.5 volt is immediately cancelled by the 2k ohm resistor. So okay. So we agreed that here we have 0 and here we have 0. So the effect of this and this cancel each other. So it's like 0.5 volt plus 2k, some current flowing into I. Say the current is this. So 0.5 plus some current that flows into I is equal to 0. So the addition of these two effects should be equal to 0. There's no effect. So I went from 0 up to 0. So I did nothing in this branch. So let's separate everything. So minus 0.5 is equal to 2k I. So I is equal to minus 0.5 2k. And this is gonna be equal to something, some number. I'm gonna call it I again. So the current in here is I calculated it, and it's a negative value. So actually its direction is this. In the back of our minds, the current is flowing in the opposite direction, down to the ground. But I'm gonna keep with the convention that this is I and it's negative. Now, I is gonna move like this, and it's gonna go into this node, but nothing flows into the op amp. The current flowing into the op amp is 0, so the current IA goes and continues upwards. Okay, so this same current, so sorry, excuse me. So this current right here, which is I, is exactly the same as this one here. And what I can do is that I can find this voltage. How? Let's call it VO1. So I can find VO1 because this is 0, V equals 0. So I'm gonna say that VO1, so I'm gonna say that 6k times the current I, this is gonna give me the voltage difference across VO1 minus 0. Right? The voltage difference between this and this is exactly equal to the voltage drop across the 6k ohm resistor, which is 6k times I. By voltage drop, I mean the voltage across the resistor, the voltage that the resistor takes. So VO1 is equal to 6k, so times 10 to the 3 times the current that I calculated in here, minus 0.5 times 2k. So do this calculation. So I guess if you multiply this by 6, you get 3 times minus 0.5. So I is equal to not I multiplied by the resistor. So the voltage VO1 is equal to this. So minus 1.5 volt. So this right here is minus 1.5. Okay. I finished my job for the most part, I suppose. Yeah. Okay, so we have decided that this is minus 1.5, and this is gonna be now the Vn of the other op amp, and this is the Vp of the other op amp. Now, what catches our attention is that this Vp, this Vp is immediately plus 2 volt, because the only thing connected between the ground and Vp is this source, which is the 2 volt. So it's like I start from 0, go up plus 2, and then reach Vp, which is, so Vp is equal to plus 2. Okay. So if Vp is equal to plus 2, I can transfer this into Vn. So, okay. So I can transfer this into Vn, so, I'm sorry, what? Okay. And Vn now is equal to plus 2. Okay, now if Vn is equal to plus 2, I can apply KCL in here, because I know this is VO, and I know the value of this, and I know the value of this, so a KCL would be simple at Vn. So the current like this is 2 minus 1.5 divided by 2K plus 0, nothing flows into the op amp, plus 2, the current in here, 2 minus VO على 4K, this is all equal to 0, and I can multiply everything by 4K, so I have 4 plus 3 and plus 2 minus VO, this is equal to 0. So VO is equal to 4 plus 3 plus 2, which is equal to 9 volts. And the answer is B, 9 volts. This is everything regarding the operation amplifier. It's really two simple rules. The Vn is equal to the Vn is equal to Vp. So on the two terminals of the input, the voltage is the same. And the second rule is that no current flows into the op amp. No current goes into the op amp, because inside the op amp it's infinite resistance. It's an open circuit. وإذا بدكم تتخيلوا, which is it's not true, but it's funny. It's that if you put current into the op amp, you're gonna burn it. رح تحترق. إذا بتحطوا فيها كهرباء بتحترق الop amp. It's not true, but it's funny. It's a funny thought. The reality is that the operation amplifier has a open circuit. So because it's an open circuit, current should be equal to 0. It can't jump from here to here. This is the idea. You're obviously you're not required to know this by EECE210, but this is the concept of an op amp, which is really important for later. Problem 10, capacitors. And problem 10 asks us to find the equivalent capacitance as seen from terminals A and B. So if I were to be a person in here and I see the capacitance, what would I see? Okay, what would I see from the terminals A and B? Now immediately I see this is a hanging wire, right? Like suppose I give this circuit a current. This current will pass in here and it's gonna circulate like this, but it can never escape. So actually current never comes in here. It's a hanging wire. I have no return. Like the current goes in there but doesn't ever return. So this portion of the circuit in here, this portion is useless. I can cancel it. And let's cancel it. So this right here doesn't exist. Okay, so my entire circuit is this box. So this, no, basically. Now, for grouping of capacitors, you know that grouping of capacitors is you use equations that are reverse resistors. So if I have two capacitors in parallel, I don't do C1 times C2 over C1 plus C2. This is for resistors, and I'm in parallel. So I use the other formula, which is series. So I add capacitors if they are in parallel, which is the case in here. So 10 and 8, they're in parallel. I add them. Capacitors are just inverse of everything. So 8 and 10, this is gonna be 18. So it's like I cancel this and I cancel this and I get like this 18. I'm gonna go back to it later, so keep it in the back of your mind that this portion right here is 18. Okay, now what can I say about this in here? This looks like a familiar structure, doesn't it? From quiz 1 material, if you remember well, this is delta. This is a delta. This in here is a delta. Why? Because I can draw it like this. This is 40, this is 50, and this is 30. This is a delta formed by capacitors because these nodes are the same, so I can group them into one point. This is delta. Now, what can I do with this delta? I can transform it into Y by saying this C1, C2, and C3. I can transform this delta into Y. Now, how do I do this? What's the formula? You can have a formula sheet, and the delta to Y formula is included in the formula sheet, but remember, I'm working with capacitors. Everything is reversed. So, to find the Y of a capacitor, I apply the delta formula. So, C1, it's gonna be the multiplication of everything. So, 40 times 50 plus 40 times 30 plus 30 times 50. So, I multiply every two pairs of capacitors, and I have 3 combinations of those. I multiply everything in pairs. I multiply everything in pairs and consider all the combinations, and I get the numerator. And this goes on for all the other values. Now, for the denominator, I need to find what faces C1. So, example, I'm here and I look in the direction of C1. I face 30. So, like this. I face 30. So, I'm gonna put 30. Same goes for C2. 40 times 50 plus 40 times 30, blah blah blah. Divided by C2. Now, what do I see from C2? If I go like this, I see 50. And then finally, I have C3, which is equal to multiply, add this same numerator basically. And if I'm at C3, what do I see? I move, and the first thing I see is 40, so 40. So after plugging in these numbers, we're gonna find the following. Our circuit will become A, B. Remember, these two were in parallel, so I combined them into 18, and then I have in here 20. It's still the same. And now what happens? I transformed the delta into a Y, so capacitor, and I originally had a capacitor like this and a capacitor like this. So the value of this capacitor right here is 156.667, which is C1 after you put this in your calculator, and the value of this is 94, and the value of this is 17.5, which is from your formula. This is 10, this is 20. Okay, now the second step is to combine these in series and combine these in series, and to combine them we use the parallel connection. So combining these is 94 times 10 over 94 plus 10. And same goes for the other branch. They're also in series, so I apply the same formula. So the image now is gonna look like this. The image now looks like this. Sorry, and I have this other branch in here, so this is gonna be 9.038, and this branch right here is 17.09. And these two are in parallel, I can add them. And when I add them, I get one capacitor, which is in series with this and in series with this. Now, after I consider that they are in series, so I apply the parallel connection to them, this combination as a whole is parallel with 18, so I'm gonna end with something like this. This is C combined, let's say, and C combined is parallel with 18, so the equivalent capacitance is C combined plus 18. So the circuit I'm gonna do it all in one shot. So I have, these are in series, so I have 1 over 20 plus 1 over 9.038 plus 17.09 plus 1 over 156.667 inverse. Because remember, the formula went like this. Sorry, not like this. The formula went like this. 1 over C equivalent in case of series is equal to the sum index I of 1 over Ci. And then I inverse both sides. Okay. Now this is the value of the capacitor of the series capacitor. So C combined, but then the C combined is parallel with 18. So if it's parallel with 18, I add plus 18. This is C equivalent. Now put this on your calculator. You get it's the answer in here. It's answer A. You C equivalent. You get C equivalent, which is 28.56 microfarad. How we get it? We transformed delta to y and did all this stuff. And we ended up with this equation. Put it on a calculator, you get 28.5. Problem 11. Sorry. The voltage across a 200 millihenry inductor. So this is an inductor which is 0.2 Henry. Same as 200 millihenry. And across this inductor I have plus minus Vt, which is given by this equation for time greater than 0. But for all our purposes, time is positive. I can't analyze a circuit in negative time. So for time equal to 0 is a good thing to know. So determine the value of the current that is passing through the inductor between times t1 equals 0 and time 2 equal 1. Assume I0 equal 1. Now, I need, if I have this configuration, I need to find the current in here, which is also a function of time. I need to find the current IT. Now, if you remember, which a golden formula for inductors is that V equal L di by dt. So I'm gonna do a quick derivation, but basically use the same formula for current from the formula sheet. So di by dt, this is gonna be equal to V over L, which is 1 over L Vt. Now I have a derivative to reverse its effect. I do an integral. So integral from t0 to t1. There's 1 over L outside because it's a coefficient. I kick it out of the integral. We get Vt dt plus some constant, I0. Now why do I add plus constant? Because if I do an integral f of x dx, this is gonna give me big f of x plus c, but I don't know this c. Well, actually, this c is an initial condition, which is I0 in our case. So always the formula is I equal 1 over L, integral from some time to some other time, the voltage dt, and then after I finished all of this plus I0, so like this, plus I0. Okay, so current is equal to 1 over 0.2, integral from time equal 0 to time equal 1. Now Vt is equal to 3t squared plus 2t plus 4. So 3t squared plus 2t plus 4 dt plus the initial current I0, which is 1. Okay, so 1 over 0.2 is 5, yeah, 5. And then I do the integral, so 3t squared becomes t cubed. Basic integral, I'm not gonna explain this. And 2t is t squared, and then 4 is 4t, and evaluate from 0 to 1, and then plus 1 at the end. So 5, well, at 0 everything cancels, so I'm just gonna substitute 1. So 1 plus 1 plus 4 plus 1. So this is gonna be equal to 5 into 6 plus 1, so 30 plus 1, so 31 amperes. And the answer is 31. Now, okay, mutual inductance. Now, before I go into this problem, it's deviously looking simple, but it really isn't. There's a trick. Before I get into this problem, I really want to jump to this problem, which really explains mutual inductance really good, really better. It makes you grasp the idea. So in problem 13, they're asking you to write the the mesh equations for the following circuit. So if I'm gonna do mesh currents, I'm gonna call this I1, I'm gonna call this I2, and I'm gonna call this I3, and I'm gonna do mesh equations. Now, this is a really good sample to explain mutual inductance, and I know that some of you have seen 3 mutual inductances in a circuit. Now they're gonna think that oh, the signs are really bad, really, and I agree with you. Dealing with 3 mutual inductances is long, but I really believe that if you can understand the idea behind 2 mutual inductances, you can understand the idea behind 3. Because if I had an inductor and it's mutually coupled by M1 and M2, well, you're gonna take L di by dt, the voltage across the inductor itself, plus the effect of the other inductor, plus the effect of the other inductor. So if we have 2 mutual inductances, this is enough. But if we have 3, you're gonna add the effect of the other new mutual inductance, and the sign of which is really covered in this example. Back to our problem. So the idea of mutual coupling and signs relating to this mutual coupling is given by the dot convention. So if you notice, every coil or every inductor has this dot. What is this? The idea behind it is that it signifies the dot convention. What does the dot convention say? Okay, let's see. Let's do mesh 1. So first thing I see is 9. So 9 I1 minus I2. This is simple. This is not really my point. My point is to reach the inductor. Plus 5 I1 plus I reach an inductor. Forget that this inductor is mutually coupled. What's the voltage across this inductor? Assuming passive sign convention. So if current enters like this, I1, so I have plus minus. So I hit plus 3, which is L of inductor 3, di1 by dt. Why? Because the formula is V equal L di by dt. L is 3, and di by dt, I is the current passing through the 3 Henry inductor. Okay. Now it's time to look at the mutual inductance. So the idea is that I finished with the voltage in here, but I need to account for the voltage of the dot, the voltage of the mutual coupling between 3 Henry and 2 Henry. So what I do is really simple. I'm working at 3 Henry, but there's mutual coupling. There's a mutual coupling to 2 Henry, so I instead focus here. I go to the 2 Henry. I go in here. Now I ask myself, what is the current that is flowing into the dot of the 2 Henry? So the current that flows into here. So I want to enter the 2 Henry from the dot side. So this is wrong. I don't want to enter like this. I want to enter like the red arrow. I want to enter into the dot. The current that enters into the dot is I3 minus I2. It's simple to see it from quiz 1, right? My quiz 1 material. So the current that's flowing into the dot is I3 minus I2. So simply the current that is flowing into the other resistor I carry. So I'm gonna say this is mesh 1, and my mutual inductance is 8. So I get this 8 and put it in front. So 8. I'm not gonna include the sign yet. I'm not gonna include the sign. We're gonna see. D by dt. Now, sorry, the D by dt is for this current that is entering the dot of the other inductor. So I3 minus I2. Now that I have decided on the current that is entering this dot, I go back in here. And since the current entered the dot, I'm gonna have a plus at my dot. I'm gonna have a plus at the dot I'm working on. So plus at this dot and minus at this dot. But remember, how did I perform my KVL? I performed it like this. So the first thing I hit is a minus. The first thing I hit is a minus, so the answer in here is minus. Sorry. The answer is here is minus 8 di3 minus I2 over dt. Now, maybe this is confusing, but it's really like I tried to make it to make the wording as simple as possible. So I need the current that flows into the dot of the other inductor. So in this case, the 2 Henry, the current flowing into the dot is I3 minus I1, I3 minus I2. And then since I chose the current to flow into the dot, I place a positive sign at the dot of the inductor I'm working on right now. This is all equal to 0. Now for cosmetic purposes, I really don't like the plus sign here, so I'm gonna change it into minus. So what I'm gonna do is flip the sign inside and flip the sign outside. So my I3 minus I2, but negative. So I2 minus I3. Sorry, I mean this. So I2 minus I3. But I flip the sign inside, so I flip the sign outside, so plus. This is for cosmetic purposes, so I change the coefficient into a plus sign. Now mesh 2. Mesh 2 across I2, I have 9 I2 minus I1. 9 I2 minus I1 plus the inductor. The inductor, now I forget about mutual coupling and I focus on the inductor itself, which is LdI by dt, I being the current that is flowing regularly through the inductor. So L, so 2 d by dt. Now what's the current flowing into the inductor? It's I2 minus I3. So I2 minus I3. So think of it as a resistor, but the formula is a little weird. So I2 flows like this, and I3 flows in the opposite direction, I2 minus I3. Now, considering the mutual coupling, let's consider the mutual coupling. I can't forget that I have mutual coupling. Let me put back this I3. And I have a mutual coupling, so and I'm working across this 2 Henry inductor, so because I have mutual coupling, I go back and focus on this 3 Henry resistor, 3 Henry inductor. I'm sorry, 3 Henry inductor. So I go back and focus on the 3 Henry inductor, and I decide what's the current that is flowing into the dot. I want the current to enter from the dot side. Now the current that enters from the dot side, here we have I1, which is entering from the opposite side of the dot. So minus I1 flows into the dot. So the mutual inductance is 8. So I'm gonna put 8 without a sign. D minus I1 over dt. I1 being current flowing into dot of other coil or inductor. Okay. Now that I've decided on the current that is flowing into the dot of the other inductor, I decided that the current flows into the dot, so I go back in here and place a plus sign in here on the dot. I place a plus at the dot, so necessarily the other terminal is negative. And continuing my KVL, I was going like this by I2, so I hit minus first, so minus. And then finally I continue to 5 I2 plus 5 I2. I hope this second example makes it better for you. Now for cosmetic purposes, I invert the sign outside and inside, so that outside I get a plus. But if I get a plus outside, so I invert the sign inside the derivative, so also plus. So all in all, the effect of the mutual coupling is 8 di1 by dt. Okay. This is for mesh 3, mesh 2. Now for mesh 3, which is final one, hoping that the idea of the dot product is clear by now, I get into I3, and let's start 1 I3, so I3, and then plus 3 I3, and then now the 2 Henry inductor. Forget about the mutual coupling and focus on the 2 Henry inductor. The voltage across it, it's 2, D current flowing into it, so I3 over dt. V equal LdI by dt, I being the current that's flowing into the inductor. Now, I need to focus on mutual inductance after this, so from this 2, I get back to 3, the 3 Henry coil, and when I get back in here, I need to focus on the current that is flowing into the 3 Henry inductor. So the current flowing into this, we established it before, the mutual coupling is M. D, the current flowing into the dot of the 3 Henry inductor is minus I1 over dt. Now I need to decide on the sign. Deciding on the sign, since I chose the current to be flowing into the dot of the 3 Henry, I put a plus sign at the dot. So plus sign at the dot. And by the direction I'm taking the KVL along I3, I hit the dot first. I hit the plus sign first. So plus. Now, there isn't really a need for cosmetic purposes, but depending on the question, you might need to flip the sign, because sometimes he says, put it in terms of A di1 by dt, not d minus I1. So this minus, you're gonna carry it back. Depending on the question, but the idea stands that the sign in here is plus, and you can do other mathematical manipulations in order to get the result that you want. Finally, I have the 7 ohm resistor in here, which is 7 I3 minus I1 plus 7 I3 minus I1. Hope this is clear. Hope mutual inductance is that you really overcome the thing about mutual inductance. So when I need to consider mutual inductance, I go to the other coil, I get the current that flows into the dot and put this current as di by dt, whatever I is, the current flowing into the dot of the other inductor. And then I go back into the inductor I'm working on originally and put a plus sign at the dot I'm working on. So I put a plus sign at the dot that I'm originally considering, and by the direction of the KVL, I either hit the dot or not. So the side where it doesn't hit the dot it's minus sign, basically. So these are the 3 mesh equations in here. Now, finished with this problem, I want to go back to this problem, which is the final problem. It's really important. So taking L equal 4 Henry, so this in here is 4H, and M to be 2 Henry, so the mutual coupling is 2 Henry. Actually, you know something, before I get into this equation, we had also this question. Also, I'm gonna answer it in here. Also, is the value of M equal 8H realistic, justify? We know that M is equal to K square root L1, L2. If you don't know this, it's included in the formula sheet, and also it's included in the slides. Yeah, and K is a number between 0 and 1. It's a factor. You can say it's an efficiency. Really, I'm not really sure if you can consider it like that. But K is a number between 0 and 1. Yeah, you can consider it as an efficiency, as how good is the mutual coupling between these two inductors. Now we find that 8 is equal to K square root L1 L2. So 8 is equal to K square root 2 times the 3. So K is equal to 8 over square root 6. But 8 over square root 6 is greater than 1. So K is greater than 1, but K needs to be between 0 and 1. And I found K to be greater than 1, which doesn't make sense. So the value of mutual coupling equal to 8 Henry is false. It's not realistic. It's really just for the purpose of the exercise. It's 8 Henry, but it's really not scientific. It's not realistic. So impossible. Back to problem 12. We've discussed the dot convention from problem 13 earlier, so moving on to problem 12 should be easy. Yeah, so the thing is, they're asking us to find the total energy stored in the circuit, which is W. And we know that W, for the case of coils or inductors, is equal to half Li square. But I have a problem. If I apply this formula for the 2 Henry and the 3 Henry and this 4 Henry, what about the mutual inductance? Well, I obviously can't ignore it because, well, some of the energy developed by the 2 Henry will affect the energy developed by the 3 Henry. So really, if the 2 Henry inductor is operating at a certain energy, it's gonna play around with the energy of the 3 Henry inductor. So I need to include the effect of the mutual inductance. But there's a problem. The formula is half Li square. Well, what is this current that is flowing in the mutual inductance? Well, it's not really a thing. There's no current flowing into a mutual inductance because the mutual inductance isn't a sensible thing. There really isn't a current flowing into this. So we need to figure it out. And whenever we need to find a quantity which is not a voltage, which is relating to mutual inductance, we need to consider L equivalent. Because we need to find the energy, but there's mutual inductance in there. So how about we go and replace all of this section by a single inductor that mimics the role of all of the 3 inductors and the mutual inductance in the middle. And how do I do that? Now, one way to find L equivalent, so I need L equivalent of, I have 2 Henry and I have 3 Henry and I have 4 Henry and I have I have this mutual coupling like this, which is M equal to Henry. Now the way I find and I have in here plus 5 amperes flowing. The way I find L equivalent is to get this V total in here. What's V total? It's the voltage across the 2 Henry, the 3 Henry, the 4 Henry, and the mutual related to the 2 Henry and the mutual related to the 3 Henry. So V total is, the 2 Henry one is easy. 2, so I'm gonna say 2I, whatever I is. Not really, I'm considering when I is variable, so not really a constant. So I'm not saying d constant by dt, which is 0. Let's keep it general and let I equal 5. But the general direction, so maybe I should change this. The general direction of I is this. So the positive I in this direction, so like this, plus 3 di by dt plus 4 di by dt. But now I need to include the mutual. Now let's include the mutual inductance caused by the 2 Henry inductor. So I go from the 2 Henry to the 3 Henry and notice what I get. So I have I flowing like this. So I need this current to flow into the dot. So how can I make it flow into the dot? Well, this current right here is minus I. If this is plus I, the current flowing in the opposite direction is minus I. And now that I've considered the current flowing into the dot, I create a plus in here. I create a plus at the dot of the 2 Henry. So plus, because I'm viewing the voltage like this in this direction. So plus 2, which is the mutual, d minus I over dt. But this is really complicated. Not really complicated. My target is to take di by dt because there's di by dt in here, di by dt in here. I need to take everything as a common factor, all di by dt. But this is not di by dt. This is d minus I by dt. So for cosmetic purposes, I'm gonna remove this minus sign and give it to the minus 2. So like this. minus 2 di by dt. Now, what about the mutual inductance referred to the 3 Henry? Now, to do this, I go back to the 2 Henry. The current flowing into it is positive I, so the current like this flowing into the side of the dot is plus I. I'm good. Now, so at the dot of the 3 Henry, I create a plus. So there's a minus on the opposite side. Now, I create a plus at the side of the dot. There's a minus on the opposite side, but I take the voltage like this, from plus to minus V total. So first thing I'm gonna hit is the non-dotted side. The non-dotted side is minus. So minus 2D. The current flowing like this into the other inductor is positive, plus I, so di by dt. Now take di by dt as a common factor, so V total. This is equal to di by dt into 2 plus 3 plus 4 minus 2, so yeah, 5 di by dt, which is equivalent to saying L equivalent di by dt. So by comparison, L equivalent is 5 Henry. So my circuit becomes this, 5 amperes. I replace all the mutual inductances and whatever with 5 Henry. And a resistor like this, which is 5 ohms. And what's the energy? Well, the energy is the energy across the inductor, which is half Li square, times the current I is 5 square. Now, what about the resistor? Well, the resistor is interesting a little bit because I know P equal Ri square. Let me change colors. P equal Ri square. But if I is constant, because 5 is constant, this is 5, so this is constant. No, it's not really gonna matter anyways. I'm not speaking for P to be constant really. I'm referring to the equation where it says the energy is from time equals 0 to time equal 1 P dt. But there's a problem. I'm considering the energy at a specific time. The problem didn't ask me to consider the energy from a time interval between 0 and 1, because remember, when I speak about the energy dissipated in a resistor, I speak about the energy dissipated between 2 time intervals. Time interval t0 to time interval t1, what kind of energy I dissipate in the circuit, in the resistor. So if I don't specify a time interval, I'm gonna assume that the time is instantaneous. I'm considering the energy right now at this instant. So at this instant, we're gonna have the integral from t back to also t, the same limits, but the integral from a to a of anything is 0. So the resistor at an instant doesn't dissipate energy, but a resistor across an interval, it does dissipate energy. So what am I saying from all of this? I'm saying that at specific time interval, at a t, at specific t, not an interval, the W of this is 0, and I'm not gonna add an energy from the resistor because it's 0. I'm not considering a time interval. I'm considering an instant, so W is 0. So here it's half times 5 cubed, so half times 125, which is 62.5 joule, and 62.5 is this answer. Yeah, and yeah, we solved this already, and yeah, we solved everything. So the material covered basically Thevenin equivalent circuits. There are 3 cases: independent plus independent, and dependent alone. The 3 cases, yeah, I've summarized them above. It covers source transformation, it covers superposition, operation amplifiers, the concept that the voltage at the inputs are equal and no current flows in, saturation, cascading op amps, which means I include multiple op amps in the same circuit, so cascading them, and discussing equivalent capacitances. Well, I could include equivalent inductors, but they work the same as resistors. So if you master resistors, you can master inductors. So we've considered equivalent capacitors, the energy and power stored, and finally the dot product, which is Not a lot of people really think about it in an easy way, but I hope I really did clear this gap regarding mutual inductance and the dot convention. So anyways, I hope this session was helpful for you, and any feedback would be really beneficial for us. The PDF will be included in the drive and linked in the comments and in the description. And yeah, I hope this session was beneficial, and good luck for your quiz too, guys. Really, goodbye and good luck.